Imagine we had this set of questions, so 3, and then 3 times 3, 3 times 3 times 3, 3 times 3 times 3 times 3, 3 times 3 times 3 times 3 times 3, and so on. We could keep this pattern going, adding in an extra times 3 each time. Now I've chosen to do this with 3s. I could have done this with any set of numbers. I could have done this with 2s or 4s or 5s or whatever, but I've chosen 3s for this set of questions. Now these are all perfectly reasonable questions. There is nothing wrong with them. They might look a little bit messy, but they are all mathematically valid, and they are the kind of thing that somewhere in some context we might have to do. Now the first thing we could do is we could fill in what these are actually equal to. We could work these out as numerical answers. They are times questions. We could work these out. So, to fill in the answers then, 3 for that first one. 3 times 3 is 9. 3 times 3 times 3 will be 27. We might at this point need to start using a calculator. That's fine. We could go off to the side and work it out by hand, or we could grab our calculators. But 3 times 3 times 3 times 3 will be 81. And then another one, 3 times 3 times 3 times 3 times 3, 243. And again, however we wanted to work those out, we could do that. That would be absolutely fine. Now the problem with these questions, while they are mathematically valid, they are a little bit messy. And certainly if we wanted to continue this sort of pattern and have more steps with more 3s in there, it would get harder and harder to write because we'd be having to count along with what we were doing. Having these 2 and 3 and the 4 and even the 5 isn't too bad to write down, but if we wanted to have maybe 6 or 7 or 8 or more than that, it would take us a while to write, and we'd have to be very, very careful. And the more stuff we're writing, the more likely it is that we would make mistakes. So maybe we need to come up with some sort of notation that we can use instead of having to write things in this way. And we are in fact going to do exactly that. Something is worth noticing before we talk about this notation, what this actually means. Here, for example, we have got 5 3s and they are being times together. As in, it is 3 times 3 times 3 times 3 times 3. That is not the same as 5 lots of 3. 5 lots of 3 would be a 3 and a 3 and a 3 and a 3 and a 3, and then we're adding them together. That is not what we're doing here. We have 5 3s, but they are being times together, not 5 lots of 3. So what I'm going to do is I'm going to introduce a notation that we can use to write this kind of question in shorthand. We are working with 3s. 3 is our base number, if you like, it's our focus. So I'm going to write that down first of all. Then I'm going to go, there are 1, 2, 3, 4, 5 3s involved in this particular question. So I'm going to, up in the top right corner, write a little 5 there, to say that there are 5 of them that we are timesing together. Again, not 5 lots of 3, but 5 3s that are multiplied together. Here, 1, 2, 3, 4. So this will be 3 with a little 4 up in the top right hand corner. This one here, 3 with a little 3 up in the top right hand corner. 3 with a little 2 for this one, 3 times 3. And just 3 with a 1 because there's just 1 on its own. Now what this pattern is called, this is the powers of 3. Where a power is what we call this little number up in the top right hand corner. So this, for example, will be read 3 to the power of 5, 3 to the power of 4, 3 to the power of 3, 3 to the power of 2, and 3 to the power of 1. Where the power is just the name for how many of those numbers we are timesing together. So to reinforce that, if we had something like this, say, 4 with a little 3 up in the top right hand corner, we would read that as 4 to the power of 3, and that would be 4 times 4 times 4. If we wanted, we might then work that out as a number, but it might be that we just want to be able to switch between this power notation and this more long form notation. Something like this, say, 5 times 5 times 5 times 5. Well, our number that we are dealing with is 5. And the power is how many of those we are timesing together. 1, 2, 3, 4. 5 to the power of 4. And again, notice it's not 4 lots of 5, but 4 5s that are being timesed together. And the first type of question that you might have to deal with when we're looking at powers is to switch between these kind of power form and long form types of writing something down, where this is the power form, the way of writing this question with a power in, and this is not. This is the full question. This is what we'd actually be doing if we were asked to work out the value. But the first thing you might have to do is write something as a power, or take a power and write it in full. A final bit of basic powers terminology. Power 2 and power 3 are particularly useful. There are lots of other bits of maths where power 2s specifically and power 3 specifically turn up. Because they are so important, so useful, we give them their own name. So you may often see, and I will do this, that power 2s are referred to as squareds, i.e. 3 to the power 2 could be read as 3 squared, where squaring something means you times it by itself, i.e. power 2. And power 3 is also sometimes known as cubed. So 5 to the power 3, for example, would be 5 cubed, i.e. 5 times 5 times 5. Power 2s, also known as squareds. Power 3s, also known as cubeds. Now the second thing we might need to do with powers, again for a kind of 1-mark question, is to work out the value of a power. And if you're asked to work out the value of a power, that means find what it is as an actual number. This is a question, this is also a question, we might need to turn this into an actual number and find out what it's actually equal to. Two ways that we might need to do that. For small numbers with small powers, we could probably do that without a calculator. Something like this, 4 times 4 times 4. We could probably work that out without a calculator. If we were asked to work out the value of 4 to the power of 3 then, 4 times 4 would be 16, and then times that by 4. We might go off to the side perhaps, and 4 lots of 16 would be 64. But for larger numbers or larger powers, or even sometimes if they're being generous, smaller numbers and small powers, we could turn to our calculators. And your calculator will have a button that lets you work out powers. What that button looks like depends on your calculator. There are a couple of different options. Your calculator could have any of the following buttons as its power button. It might have a kind of curly X with a little square up at the top, or it might have a Y with a square up at the top. It might have a button that looks like this, a kind of upward pointing arrowhead, or it might have this, an X and a Y where the Y is in the power position and the X is in that kind of base number position. Or I suppose possibly a Y with a little X up there. They are probably the 5 most common buttons that you might see, and your calculator will probably have one of them. It is possible that your calculator might also have its own power 2 and maybe even its own power 3 button. It will be whichever of these, but with a 2 or a 3 in this top position. If we glance at my calculator for a moment, we can see that my power button is there. On my calculator I have the X with the power button up in the top right corner there, the box. X with the empty box, where the box is showing that I would then put a power number in there. I'm lucky because on my calculator I also have the power 2 and the power 3 buttons fairly nearby. Not all calculators will have that, and it doesn't really matter if yours don't, because you can always just use the power button to fill in those power 2s or power 3s. But if they are there, you are welcome to use them. Now, whichever of these your calculator has, you will also need to work out the specific order that you need to press stuff in. Different calculators will have you do it in slightly different ways, but probably for most of them it will be as simple as press the base number, then the power button, and then the power number. For example, we'll take a question that we already know the answer to. We'll have a look at one of those ones from before, one of the ones with a 3. Well, for example, the fourth thing down on our list, 3 to the power of 4, we got 81. That's 3 times 3 times 3 times 3 was 81. If we can work that out and get the 81, then we know we're okay. What I need to do on mine is I need to type in first the 3, so that's the base number, the one that we are doing the powers of. Then I need to simply press my power button. That gives me a little flashing box there that I can fill in, and I can type in the power of 4. Your calculator may display this slightly differently. It depends what button you're using, it depends what calculator you're using, but for most of these it will be type in the base number, press the power button, type in the power, and then press equals, and on mine I return that answer of 81. On a related note, if we consider these squared powers, these power 2s, so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, all the way up to 12 squared. So that's the first 12 counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we're squaring each of them. So 1 squared, 1 times 1 is 1, 2 squared, 2 times 2 will be 4, 3 squared, 3 times 3 is 9, 4 times 4, 16, 5 times 5, 25. 6 times 6, 36, 7 squared, 7 times 7, 49, 8 squared, 8 times 8, 64, 9 squared, 9 times 9, 81, 10 squared, 10 times 10 is 100, 11 squared, 11 times 11 is 121, and 12 squared, 12 times 12, 144. Now I could carry this list on, I could carry on with 13 squared, 14 squared, and so on, but actually these will do for the point that I'm trying to make. These numbers in green, the result of taking the counting numbers and squaring them, these numbers in green are known as the square numbers. Because they are the numbers that we get when we square the counting numbers. So 13 squared, 13 times 13 is 169. 169 is also a square number. So the square numbers 1, 4, 9, 16, 25, 36, and so on. The results of squaring the whole numbers, the counting numbers. Do you need to know this list by heart? Well, not necessarily, but it is usually useful if you can recognise a square number, because a nice basic question would be, here is a list of numbers. From this list of numbers, write down a number that is a square number. And it might be that you then look at that list and you recognise 36 and you go, oh, 36 is 6 times 6, 36 is a square number, and I can write that down for a 1-mark answer. Or we could also look at the cubed powers. So this is 1, 2, 3, 4 and 5, and then we're cubing each of these. So cubing the first 5 whole numbers. Well, 1 cubed, 1 times 1 times 1, by definition of what cubed is 1. 2 cubed, 2 times 2 is 4, times 2 would be 8. 3 cubed, 3 times 3 is 9, times 3 is 27. 4 cubed, 4 times 4 is 16, times 4 is 64. And 5 cubed, 5 times 5 is 25, times the 5, 125. And again, we could carry on. We could do 6 times 6 times 6 for 6 cubed, 216, and so on. We're just going to stick with these for now, though, the 1, the 8, the 27, the 64, and the 125. And these are the cube numbers, these numbers in blue. The result of cubing the counting numbers. So again, you might have to write down from a list a number that is a cube number, and you might look for one of these, the 1, the 8, the 27, the 64, or the 125. Cube numbers, the result of cubing the counting numbers, doing the counting numbers to the power of 3. Work out the value of 3 to the power 4 plus 5 squared. Work out the value of questions mean find a single numerical answer at the end. And the only thing we could really do with this, these are two different base numbers with two different powers. There's no way we can kind of make this neater or simpler in any way. The only thing we can do is just return to that definition of a power. 3 to the power 4, for example, we could work that out as a single number, as an actual answer. And we could do the same for the 5 squared. And once we've got those two numbers, we could just do whatever the question is asking us to do. In this case, add those two values together. So 3 to the power 4, 3 times 3 times 3 times 3. Maybe we grab our calculators, put that in our calculators, and we get that that is 81. And 5 squared, 5 times 5 would be 25. Maybe we pop that in our calculators, maybe we just work that one out from our times tables, or we know that 5 squared is 25 because we know our square number list. The question is asking us to add those two together. Why? Because that's what the question says. So we've turned 3 to the power 4 into 81. We've turned 5 squared into 25, just using those definitions, and then we're going to add them together to get our final answer of 106. And there is our answer overall. For any of these questions, if we are asked to work out the value of, turn the powers into numbers, and then do the calculation with them, add, take, times, divide, or whatever else it might be. Powers of 2 and powers of 5. There is a times, but that shouldn't change anything. But we're going to work out the 2 cubed first of all. 2 times 2 times 2 is 8. Then we're going to work out the 5 squared. 5 times 5 is 25, and then we are going to times those two together because that's what the question told us to do. And we're going to do 8 times 25, and perhaps on our calculators, perhaps not. 8 times 25 is 200, and there is our final answer. And again, work out the value of just means find a single numerical answer. Now the final type of powers question to work with is one that looks like this. Simplify to a single power. And then, for example, 2 cubed times 2 to the power 6. First thing to notice about these, we've got the same base number. We're dealing with powers of 2 in the first part, and we're dealing with powers of 2 in the second part. That's important. Second thing we need to notice is what our answer should look like. The question tells us to simplify to a single power. That says to us that whatever answer we get out the end, it should be a power. Not a value, as in a number, it should be a power. Something to the power of something else. So what we're not going to do here is work out any of these powers. We need to start with things in power form and we need to finish with things in power form. And actually, whenever we see this word simplify in a question, it means that we are going to be rewriting it. We're going to be taking something and rewriting it in hopefully a simpler way, with less stuff in it. There are two types of these questions, these simplify to a single powers question. The first involves timeses and the second involves divides. And this is the times example, so this is our first one. Now what we're going to do with these questions is we are going to go back to the definition of what a power is. At first we're going to think about this 2 cubed, this 2 to the power 3. And I'm going to write out in full what that is. And what that means is 2 times 2 times 2. That's me writing it out in full. I'm not working it out, I'm not turning it into a number, I'm just turning it back into that kind of power form. Now I could do the same thing with the 2 to the power 6. And I could write out what that means. And that means 2 times 2 times 2 times 2 times 2 times 2. 6 2's that are being multiplied together for the power 6. And there's one thing missing from this. I've stretched out the 2 cubed into its proper full form. I've stretched out the 2 to the power 6 into its proper full form. There is a times there in the middle. Why is that times there in the middle? Because it's the one from the question. Now, hopefully, now we can see it like this. We might notice something about this. This is some 2's that we're timesing together, some 2's that we're timesing together, and actually both sets of those, the blue set and the green set, are all being times together. Well, this is just a load of 2's that are being times together. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 2's being timed together. So our final answer then would be 2 to the power of 9. And what we've done is we've taken something that's two separate powers of the same number and times them together, and we've rewritten it as a single power. This is a single power of 2 where the power happens to be 9. First key point to make. We don't need to work that out. We're not interested in what 2 to the power of 9 is, and we haven't turned any of these into numbers anywhere in the question. We have just used the definition of a power to rewrite something as a different power. The second thing that's important, you might for yourself notice a link between the powers here and the power in the answer. That's fine, and if you notice that, and doing more of these questions in this kind of way, you might start to spot a pattern. Fine, I am not going to tell you what the pattern is, because if I tell you the pattern, then that's the only thing you remember, and not why the pattern is there. If you realise the pattern for yourself, then great, feel free to use it, and as a clue, it does work, but you will understand for yourself why the pattern works. So I'm not going to tell you the pattern, otherwise it's the only thing you remember, and then you just blindly use it, and that's not helpful to anyone. We'll do another one of those. Simplify to a single power, 5 squared times 5 cubed. So again, what we're going to do is we're going to go back to that powers definition. We're going to stretch each of these out into their full form. So 5 squared is 5 times 5, and 5 cubed is 5 times 5 times 5. So I've just written those out in full. I've not done anything with them, I've not worked them out as numbers, I've just written them in full. There is a times there in the middle, that's the one from the question. And overall, we're still dealing with 5's. It's 5's all the way through, and we've got 1, 2, 3, 4, 5 that are being multiplied together. So we've got, as a final answer, 5 to the power of 5, which we're not going to do anything with. We're just going to leave it as that, because the question wants us to simplify to a single power, which that is. Now, the second type of these questions involves a divide. Simplify to a single power. Same kind of question again. We go in with some powers and we come out with a power at the end. 7 to the power of 5 divided by 7 to the power of 2, or 7 squared. First thing we're going to do with divides is we're going to rewrite these in a slightly different way. We're going to think back to that other way of writing divides that we've already seen. And I'm going to write them with that one thing over the top of another, just because it's easier to see what we're doing here. 7 to the power of 5 divided by 7 squared, where I've written them in that one thing over the other thing way of writing a divide, where that line in the middle means divide. I'm then going to write these out in full. So on the top line we've got 7 times 7 times 7 times 7 times 7, these 5 7s that we are multiplying together. And on the bottom line, 7 times 7. Now the next thing I'm going to do is I'm going to look on the bottom and on the top, and I'm going to hopefully notice that on the bottom here in this green box we have a 7 times 7. And on the top here in this green box we have a 7 times 7. Why is that important? Okay, step off to the side for a minute. Imagine I have a number, say 2. And then I times that number by 10. Well, if I times it by 10, I get 20. But then I take my 20 and I immediately afterwards divide it by 10. So I've taken 2, I've times it by 10, and then I've divided it by 10. And if I do that, I get back down to 2. So the times 10 and the divide 10 here, this bit happening in the middle, if I times by 10 and then immediately divide by 10, the times 10 and the divide by 10 are having no net effect. It's changing and then changing it back. It's doing something and then undoing it, because of this idea that timesing and dividing are kind of like opposites of each other. And if they're having no net effect, then they might as well not happen. The times by 10 and the divide by 10 might as well not be there. And this kind of idea works with any numbers. If I start with something like 3 and times it by 4, for example, that would get me up to 12, making it 4 times bigger. But if I immediately make it 4 times smaller again and divide it by 4, then I get straight back down to the 3. And the times 4 and divide by 4 that undid each other, times 4 does and then divide by 4 undoes, they might as well have not happened, and I might as well have just started with the 3. But why is this idea important to our simplifying to a single power? Well, let's have a look at top and bottom and see what's there. So now we've talked about that, what we have got here on the top, we are times it. This is a number. 7 times 7 times 7 is a particular number. We're not interested in what it is, but it is a number. And we are timesing by this green box. We times by the contents in the green box. And then we immediately divide by the contents of the green box. Timesing by the green box and then dividing by the green box is exactly the same as the times by 10, then immediately divide by 10, or whatever. The green box then is having no overall effect. It's there on the top for a times, it's there on the bottom for a divide. We're timesing by something, then immediately dividing by something, we're changing nothing, which means the green box might as well not be there. In timesing by it and then immediately dividing by it, it's having no overall effect, it might as well not be there. So we can get rid of it. But then what are we left with? Well, we are just left with, on the top, 7 times 7 times 7, and nothing on the bottom, because we've got rid of the green box top and bottom, because it's the same on the top and the bottom, and it's having no overall effect. This, though, we could rewrite as a power. 7 times 7 times 7 is simply 7 to the power of 3, or 7 cubed. And what we've done is we've taken some stuff here and rewritten it as a different single power. Now again, you might, doing a couple of these, start to notice a connection between the numbers in the question, the powers, and the power in the answer. Again, that's fine. If you notice that pattern and you seem to think it happens every time, bit of a clue, it does. If you notice that pattern for yourself, then you are welcome to use it. But again, I'm not going to tell you what the pattern is, because otherwise the only thing you will remember is the pattern and not why it happens. If you realise the pattern for yourself, you also know why it happens, and then you can use it properly. One more example just to make this point again. 9 to the power of 6 divided by 9 squared. Simplify that to a single power. We're going to write it in this one thing over another thing form again. 9 to the power of 6 over 9 squared, and then we're going to stretch these out into the full definitions. 9 times 9 times 9 times 9 times 9 times 9 on the top, and 9 times 9 on the bottom for the 9 squared. I'm going to put stuff in the boxes. I'm going to box off that stuff on the bottom and that stuff on the top, and I'm going to say, look, we've got something on the top that's not in a box. We're timesing it by that green box and then immediately dividing it by that green box. In timesing it and then dividing it, it's having no overall effect. It's doing and then undoing, so they might as well not be there and they can disappear. We are left then simply with 9 times 9 times 9 times 9 on the top, which simplifies to 9 to the power of 4 when we write it in that power form.